just take care of people here. Okay. All right. Okay, so I walk down the Speedway. I get that full-size candy bar. And you guys, in your heads, how much change you're handing me a 20 and how much change you're expecting to get back. Is everybody good? Okay. And if the amount I returned to you was $18.09, would you be, all I want to know is, would you be surprised?
No.
So for this one, the answer is definitely not surprising. So, okay, great. What about $17.57? Would that be surprising? No? Okay. What about $5.12? That would be surprising. What about $8.78?
Yes.
$12.27.
Yeah.
$19.62.
Yeah.
$14.32.
Yeah.
I mean, the last time I purchased a full size, like just went to a store and purchased a full size candy bar, might have been 20, 25 years ago. Because I just don't buy candy bars like that, right? Like if I buy candy, I'm usually buying it for you guys or whatever, right? Like I get the miniatures. In fact, I don't know the last time I ate a full size candy bar. Do you guys remember the last time you had like a full candy bar? Maybe it's like the two Reese's cup. Two-piece package of a Reese cup I would call a full-size candy bar versus, yeah.
That's like the Babe Ruth one.
What?
The Babe Ruth one that you wanted us to try.
But those weren't full-size. Those were fun-size. But they were delicious, right? Most underrated candy of all time is the Baby Ruth, just so you guys know. That's a payday.
That's a payday. Paydays. Speaking of that, you know the boosters got us paydays for after our football game. When we had like a far away game, they just gave us like boxes. Paydays.
Also, an overrated candy bar. Because why have a candy bar without chocolate? I don't get it. Okay.
I don't know if I'd even call it candy.
All right. Now, in this setting, you guys, I kind of laid the groundwork where we started with a set of expectations. Is everybody with me? Okay. And as we look at this, if I gave you this change back, the $5.12, you guys said, in fact, that if this is the amount back I gave you, that would surprise you. Why?
Very expensive candy bar.
Very expensive candy bar. Maybe. Or you might say, Meister did not give me my change back. She kept $5. She kept $10, etc. Yeah? So, this isn't surprising at all. This isn't surprising at all. The rest of these are surprising. Though if you got this one, you wouldn't accuse me of taking your money. I wouldn't think. If you got this amount back. This was surprising in a different direction, right? Okay? And so, we started with this, like, preset expectation. So, like, when we talk about what does it take to surprise you, okay? Something is surprising if surprises happen if our expectations aren't met. Right? We usually, in order to be surprised, you need to have some sort of expectation. Okay? So now let's say the question is no longer about the amount of change you got back, but whether or not you accuse me of stealing from you. Is everybody with me? If you got $18.09 back, would you accuse me of cheating? Stealing? $17.57? $5.12?
Yeah.
$8.78?
Yeah.
$12.27?
Yeah.
$14.32?
Yeah.
Some of you would change your mind. You would not accuse a teacher of stealing from you for this one, even though it's surprising, right? It's not enough for you to be like, she a dirty, rotten thief. Because the consequences of you being wrong on this is a big deal. Yeah, you accusing a teacher of stealing, right? Okay, so, all right. So, in Unit 7, we took our p hats or our x bars and we used them to make estimations. Unit 8, we're going to take our p hats and x bars again, and what we're going to do is test a previous claim. Okay? So, as we look at each of these different values, you guys were solid about this one, this one, this one, this one, this one, this one, and then this one's kind of like, I'm like, it doesn't feel right, but is it close enough that we might be like, I'm not going to make a big deal about it? Is that like a good way of thinking this through? Okay? All right. Now, inside your head, every single one of you, I had you set an expectation. What is the price of a candy bar? So, you guys tell me. What did you guys think the price of a candy bar would be? $2.50? $1.57. Great. Anyone different than either of those two numbers? $2. In my head, it feels like it should be about $2.25, but that's adjusting from inflation back when I was your age, when candy cost like $1. Like a full-size candy bar was about $1, as was a gallon of gas. So I was like, it's probably kind of in that kind of idea range. Okay? Everybody good? Because I did pay less than $1 per gallon for gas when I was your age, because I'm old. Okay, so average cost of a candy bar, in your head, you're kind of like, oh, I think it's about, and so let's see, we had a $2.50, we had $1.57, $2. I'm going to do $2 because that seems to be about the midpoint of what you guys said. Okay, so my opening assumption might have been that the true mean of all the prices of candy bars is about $2. And then we got to decide, did the cost of each of these candy bars make us question whether or not Meister's stealing from you? If the mean cost is is $2, what's the anticipated change? You guys would have expected to get back 18, right? And so 1809, not surprising because it's pretty darn close to the $18 you expected. Close to what you would expect. You guys get the general vibe of this. Okay, so if our sample value is close to our expectations, we can say, nothing crazy is going on here. But if our sample value is, say, far away from our expectations, like these ones, that's what makes us decide, something weird's going on here. I don't like it. I'm going to make some sort of different conclusion than what I assumed. So the question is basically, I start with what I assumed. Then I say, could I actually have gotten what happened? Did what actually occur, could that have happened? And then we make a decision after that. Okay? So, we're going to do something called a hypothesis test. Sometimes we call these significance tests. Okay. Guys, we have lots and lots and lots of different samples I'm going to show you for significance tests over the next few days. Okay? We're going to start with what's called the traditional method. Okay? The first thing you will always do is write hypotheses. We will have what we call a null hypothesis. And we have an alternative hypothesis. Okay. So we're going to start with our two hypotheses. One is we're going to assume the null hypothesis, and then we're going to say, could this sample have happened if that null hypothesis is true? Okay. If the sample could have happened, that's good evidence that the hypothesis is true. If the sample could not have happened when the null hypothesis is true, we can assume that the null hypothesis isn't true, which means the alternative will be true. Okay? So if what actually happened could occur, null hypothesis is true. If what actually happened couldn't occur or is unlikely to occur, That's when we say the null hypothesis is false and conclude the alternative hypothesis. Okay. So we're going to, after we write our hypotheses, we're going to sketch a sampling distribution. We have two that we could possibly sketch. Hopefully they won't look too unfamiliar. Either a z distribution or a t distribution. And we're going to define, when we sketch these two distributions, we're going to define what unlikely is. We're going to create something called a rejection region, which will make a whole lot more sense when we actually do a few examples. Okay, but we just said if our sample is unlikely, we reject the null hypothesis and conclude the alternative. So your rejection region is which samples will make you reject the null hypothesis. Okay? Then you're going to figure out, well, what is the t statistic or z statistic for your sample, and use that to make a conclusion. Okay, let's do, that's very theoretical, and doing the theory really fast to make more time for lots of examples, because examples seem to be what made students pick it up last year. Okay, so I'm going to let you guys read this real quick. And the first thing we're going to do is write our null and alternative hypotheses. Okay. All right. The first rule about writing hypotheses is that the hypotheses will either be about p or mu, depending on if this is about a proportion or a mean. This is about the percentage of defective computer chips. Is everybody with me? All right, if this is about the percentage of defective computer chips, percentages are proportions. So my hypotheses are going to be about P, the proportion of all computer chips that are defective. So both of these will have a P, start with P. And then our boundary of our hypotheses is the claim that it's 2%, yeah? And my alternative, so when we write our alternative, and the question is going to be worded in such a way of saying, at the very end we can say, is this enough evidence to say the defective rate is higher than 2%? Okay, that's what. If we're trying to say, do we have enough evidence that whatever we want evidence of, that's my alternative hypothesis. And my null hypothesis is going to be everything else. Is everybody with me? Okay. Now, if P is not greater than 0.2%, what could P be? Less than or equal to 2%. So that will be my null hypothesis. The null hypothesis is the one that will have an equal to. If it, whatever has an equal to, that one goes in the null. Is everybody okay? All right. Now, from here, we're going to sketch the sampling distribution, which, remember how we did z intervals when what we were doing was proportions? That tells me, since this is a proportion, that we're going to draw the graph of possible z's. Okay, so sketching this sampling distribution, and then it says determine the critical value and shade the rejection region. All right, so our reasoning process is that if our sample is unlikely, we reject the null hypothesis. It's always going to come back to, if our sample is unlikely, we're surprised our opening expectation is wrong. Okay? So we have to talk about what do we mean by unlikely? So we kind of have to say, how unlikely does our sample need to be? And the answer to that is, it depends. But you will be told. Okay? And the answer to that is what we call the level of significance. And we use the symbol alpha, the Greek A alpha, which sometimes you'll see written like this or like this. Okay? That's your significance level. Okay? So in this particular one, I say a 10% level of significance. So my alpha is going to be 0.10. Are we still good? All right. So the next thing we're going to do is we're going to pick a point and shade our graph. The way we shade that graph is always going to match the alternative hypothesis. So, looking at my alternative hypothesis, should I be shading the right side or the left side? The right, because it's greater. And how much do I want to shade? What I shade is whatever that alpha is. So if I'm doing that, like right and 10%, I'd be give or take about here. And this area would be 0.10. We call that region the rejection region, okay? And the critical value is this value on the z-axis that gives me that. Can you guys, at this point, I feel like we should be pretty good at what is that value? How could we find this using our calculator? It's normal. We don't have a z-CDF. We have a normal CDF. We also have an inverse norm, right? Which one? You do inverse norm. So tail to the right. Or just recognize that this is also 0.9, right? Like, especially because later on when we do these with t's, you don't have that option. 1.282. So this test. Hi. I'm currently giving notes. No, I'm giving them notes though. He'd miss instruction. Okay. Yep, bye. One of you owes me. Okay, you guys remember the whole idea? If our sample doesn't meet expectations, that's what makes us say something funky's going on. The ones that don't meet the expectations are the ones in here. Which are the ones, so we're going to reject when z is equal to 1.282. Okay, so here's what we could do. Eventually what we're going to do in like 2 minutes, we're going to calculate the z statistic, the z-score of our sample, and say that z-score of our sample, is it in one of these ones where it meets expectations, or is it one of these ones where it doesn't meet expectations? Okay, so we're just saying, where does our sample fit within what we would expect to happen? Everybody good? Now, to calculate the z-score for your individual sample, This is on your formula sheet. It looks like this. You're going to do p hat minus p over the square root of pq over n.
What is that PQ minus N?
No, over n. And I would put it actually over n, but I'm trying to write it just as it's written in your formula sheet here. Okay? All right. So from here we got to know, well, what's p hat? P hat's the value from my sample, yeah? What do I know about my sample? 18 over 500. That's given to me up at top, yeah? So my p hat is 0.036. And then the P I'm going to use is that null hypothesis P. So I'm going to do 0.036 minus 0.02 over the square root of 0.02. If P is 0.02, Q would be 0.98 divided by 500. If you're typing this in the calculator, my recommendation is that you use that horizontal fraction bar by hitting alpha y equals. What are we getting when you're typing this in, guys? I'm sorry?
The interruption, Vivi Mikes, please report to the main office. Vivi Mikes, please
You did
report
not
to the
get
main office.
2.56. You definitely got. Oh wait, no, you did. Was it two? It wasn't 2.25.
I also got 2.56.
Okay. I'm maybe remembering a different question.
Question you. What do you mean?
Okay, you guys. Is that one of the crazy? Is that one of the unexpected samples or the expected samples based on our picture? Here's our expected. Here's our unexpected. Where does this fall? It's unexpected, yeah? Okay, so it should not have happened if my null hypothesis is true. So what are we going to do? We are going to reject the null hypothesis. We're going to reject whenever z is, that should be greater than. Whenever z is bigger than 1.282. So what I would expect is that you would say reject because, and then show that p-value being bigger than that critical value. I'm sorry, that z statistic being bigger than that critical value. All right, something I forgot to mention up top. We have a claim. What was the original claim? Was the 2%, yeah? The 2% being true. So you guys with me that my claim is my null hypothesis. So on your test, I will specifically say, state your hypotheses and indicate which one is the claim. So you want to be able to do that for each one.
I'm sorry, what is the difference between the null and the alternative?
You assume the equal to part. So you assume that the null is what you assume. The alternative is what if you have evidence that what you're showing evidence for. So at the very end, the question is this enough evidence to say that their claim is incorrect? We want enough evidence to say higher than 2%. In reality, you should think about the null will always have the one that has the equal to it, okay? And the alternative is always going to be the opposite of the null.
How do we get the 0.1 on the right and the 0.9?
Because I gave you, so the reason it's shaded to the right is that the shading will always match your alternative hypothesis.
Okay.
So since my alternative was greater than, I have a right, we call it a right, would be called a right-tailed test, because the alternative is a greater than, okay? Which means I'm shading the right tail, and then the 10% is that level of significance I would give you in the question. If I don't give this to you, you can assume 5% every time.
So since 10% is bigger than 2%, that's why we put it to the right.
No, not at all. Because this, like, it's because this is a greater than sign. That this 10% and this 2% are not of the same thing. This is 2% of defective computer chips. This is 10% of possible samples. So they're two very different percentages.
So where you put it is based off the sign.
Where you shade is based off of the sign. The amount you shade is based off of the level of significance. Okay? I promise we're going to do lots of examples to help you guys kind of through this reasoning process. This is one of the harder abstract logical processes that we use. Okay? All right? So, the last thing we're going to do, make your conclusion in the context of the claim. All right, we just said we're going to reject, and when we do, we reject the null. So it's almost like I'm drawing an X through my null hypothesis. I just rejected it. So we're going to say we reject the claim, and therefore we can say more than 2% of the computer chips are defective. There we go. Let's look at this one. All right. A news program suggests that the proportion of people who shower in the morning is greater than 40%. So as I look at that, the first thing I'm going to write down is, here's what I got. P is greater than 0.4. That's my claim, yes? All right. We take a random sample and find that of 350, 122. So that's my p hat. And this would be an example. I didn't give you a level of significance, so we're gonna use a 5% level of significance. Okay. All right. So I have two hypotheses. This P is greater than 0.4 is going to be one of my two hypotheses. Is everybody with me so far? Okay. And so does P is greater than 0.4, does that have an equal to in it? No, so it will be my alternative hypothesis. So what would be the null? Everything but that. So P will be less than or equal to 0.4. Okay? So there's my sampling distribution. Again, if this is a P, it's automatically a Z. And so mean 0, standard deviation 1. Okay, am I shading right or left? Am I shading the right tail or the left tail? Right. The right tail, because my alternative says greater than. And how much should I shade? 5%. Perfect. You guys are doing great.
Wait, why is it 5%?
5% level of significance.
Is that just the default if you're not given one?
Correct. If I don't give you one, 5% is always a reasonable one to assume. Okay? So our rejection region, we're going to reject when Z is greater than, and we got to figure out what is that boundary. And this is where we use our calculators, yeah? We're using inverse norm.
One point
1.645 sounds great. Okay. Next, we find our z statistic. We got to figure out what is 122 out of 350, y'all. I'm sorry, 349. Thank you. So, I'll do my sample value minus my boundary value. You guys, I get my z to be negative 1.948.
Why is it 1.6 want to be 0.5 and 9 for that?
No, you're using the value of p, not the alpha.
Oh.
You're going to use the hypothesized p. These two values will always match.
And then the Q is just like
1 minus. Mm-hmm. Hey guys, is our sample in the rejection region or the regular region? Regular. So we are going to what? Fail to reject. In a different color here. Because negative 1.948 is not greater than 1.645. So you're going to compare to that rejection region that you kind of set up here. My claim was, so if I'm not rejecting the null hypothesis, the alternative isn't true. The null is what's true. If I'm not rejecting the null, it's true. Okay, this is a huge departure from, anyway, AP. So, all right, so my conclusion here will be, we can say, I'm not rejecting the null, but the null is true, yeah? We can say the claim is incorrect. Because P is less than or equal to 0.4. Because we're not rejecting the null, and we're saying the null is true. One last thing. This calculation, I do give you the formula for it, but I want to show you. If you go to your calculator, if you hit stat and arrow over to test, just like the shortcut, before the shortcut for anything with proportions was the 1 prop z int. This time we're going to choose the 1 prop z test. The difference is if I'm trying to do a confidence interval versus I'm trying to do a test. So go ahead and pick the 1 prop z test. That p sub 0 it asks for is asking for the p of the null hypothesis. It's asking for what's going on up here. You put in the 0.4. The x it's asking for is your number of successes, which in this case was 122. The n, you're going to put your sample size, which was 350. And then you want to make it so this whole row is choosing which alternative hypothesis are you using. So because our alternative hypothesis in this one is greater than, we're going to have that greater than sign highlighted. Then you can go down to calculate. And you guys can see a very, very close Z statistic. It's a little bit different because our P hat was rounded, so it's not quite the same, but pretty darn close. Okay? We will do more practice with these tomorrow.